my name is Matthias Bentert. I'm from the University of Bergen, and today I'm going to talk about our paper, Exponential Time Approximation Schemes for Vertex-Ordering Problems. This is joint work with Fedor Fomin, also from the University of Bergen, Tanmay Inamdar from IIT Jodhpur, and Saket Saurabh from IMSC. So let's start, and let's talk about vertex ordering problems. In a directed or undirected graph, the problem is of the following type. We want to order the vertices linearly in order to minimize or maximize a certain objective. The most famous example maybe is feedback arc set. Here we want to minimize the number of backward arcs. And the directed cut width is for each of these vertical cuts, we want to minimize the maximum such cut. And here we only count the backwards arcs in the directed setting. And similarly for the optimal linear arrangement problem, we want to minimize the sum of all of these cuts. So just as an example, we have here two orderings. I have marked all of the forward arcs blue and the backward arcs red. And the feedback arc number of this graph, that is also depicted here in the top, is 1 because this ordering at the bottom shows that there is a way to have only one backward arc. And as we can see, there is a directed cycle from W to U to V to W. So the feedback arc number is at least 1. Similarly, we can take the same ordering to compute the cut width. Also, this is minimized here. The minimum cut width is again at least 1 because we have a directed cycle, and it's also exactly 1 because we have a ordering where every vertical cut has size at most 1. And for the linear arrangement problem, here we sum over all cuts. So in the top ordering, we would add 2 plus 3 plus 2, which is 7. And there is a better solution, again, the slower one, where we have a cut of size 3. And here I want to mention that instead of maximizing all of these sum cuts, or the sizes of these cuts, we can instead think of it as taking the length of all of these backward arcs and summing all of these lengths. So here this arc has length 2, this backward arc has length 2, and this backward arc has length 3. And these are two very well-known equivalent definitions. Okay, so now that we are on the same page, what vertex ordering problems are, let's talk about our results. And they are listed here in this table for feedback arc set, directed cut width, directed optimal linear arrangement, directed path width, and optimal linear arrangement in undirected graphs. We have the following approximation factors. For feedback arc set, a 1 plus epsilon approximation in better than 2 to the n time, but how much better we are compared to 2 to the n depends, of course, on the epsilon. For cut width, we have a 2 approximation in 2 to the w omega n over 3 time. Omega here is the matrix multiplication exponent, and this here is roughly 1.78 to the 9. For directed optimal linear arrangement, we have a 2 plus epsilon approximation that is better than 2 to the n. In the undirected setting, we have a 1.5 plus epsilon approximation. And for directed path width, we have a 2 approximation in 1.66 to the n time. Just mention here, whenever we don't state the undirected problem for feedback arc set, that the undirected problem is trivial. It's just feedback edge set, which is polynomial time solvable. And for undirected cut width and undirected path width, we have the same results as for the directed setting. Let me just briefly mention that we also have results for the weighted setting, where edges can be weighted. And for all of these problems except for path width, the best known exact algorithm runs in 2 to the n time, and for path width it runs in 1.89 to the n time. So we can see we beat the running time for all of these exact algorithms, but of course we have some approximation and not an exact algorithm. That's the trade-off here. Okay, let's now see how we achieve our results, and the main hero in our story is the following problem called minimum k n minus k cut, or in the directed setting, the directed minimum k n minus k cut. And here the problem is we want to find a subset of vertices, let's call this L, such that in the undirected setting, the number of edges between L and the rest of the graph R is as small as possible, while the size of L is exactly k. And in the directed setting, we want that the number of arcs starting in R and ending in L is minimized. But again, the size of L has to be exactly k. And one of our main lemmata is the following. Minimum k n minus k cut, and also in the directed setting, can be solved in this time 2 to the omega n by 3, which is better than 2 to the n. And how do we achieve this result? We first partition our vertex set V into 3 sets of equal size and completely arbitrarily. And then we build a new, this should say weighted graph H as follows. We take any subset of one of these 3 sets and assign a vertex to it. So here, since we have 3 vertices, this would give us 2 to the 3, 8 different vertices. And each of these vertices represents a subset. Let's say these 2 vertices here are represented by this 5th vertex. And maybe these 2 vertices in the second are represented by the 7th. So the number of vertices is roughly 2 to the n over 3. And now we make H into a complete tripartite graph with weights. And the weights are as follows. For every vertex, the vertex weight corresponds to the number of arcs from vertices in one of the 3 parts, the part we are currently considering, starting not in the subset represented by this vertex and ending in this subset. So here we have one edge going from the outside to the inside, and here also we have one edge starting in the outside going in the inside. Edges from the inside to the outside are not counted. And for edges between 2 parts, we do basically the same. So let's say we want to compute the weight of the edge for this red subset and this blue subset. Then we take all of the edges that start in the left side outside and end in the right side inside. There's one of these. And all the edges that start on the right side outside and go towards the inside left side. And there are none of these arcs. So here, in this case, our edge would have weight 1. And now the interesting thing is that a minimum k n minus k cut 1-to-1 corresponds to a minimum weight triangle in this graph H. But unfortunately, finding a minimum weight triangle in a weighted graph is APSP hard, so we don't think we can get better than n cube, and here n is roughly 2 to the n over 3, so this would give us 2 to the n. But the weights are small, and we can use this fact. So what we do is we guess all 6 edge weights, vertex weights, so 3 vertex weights, 3 edge weights, and just say, okay, let's assume our solution has exactly these weights. Then we filter H, we remove all vertices from the first part that don't have the guessed weight, or the edges between the first and the second part that don't have the guessed weight, and so on. And then we verify that there exists a solution with this weight just by finding an unweighted triangle in this large graph. And unweighted triangles we can solve in n to the omega using matrix multiplication. And since here the number of vertices in our graph is roughly 2 to the n over 3, this gives us this 2 to the n over 3 to the omega, or equivalently 2 to the omega n over 3. And this slightly faster algorithm we will now use in several applications for vertex ordering problems. And I just want to show 2 examples in this talk. In the first one, we consider the feedback arc set problem, and just as a very quick and easy introductory example, we're going to compute a 2 approximation in the same running time as the minimum k cut. And we just say, okay, we want to find a minimum directed n by 2 cut. So partition the vertices into size n over 2 sets, 2 of them, such that the number of arcs from the right to the left is minimized. And of course, this is a lower bound for the feedback arc number of the graph, because consider any optimal ordering, then there is a cut in the middle that partitions into two sets of equal size, and the number of backward arcs here is, of course, at most the number of backward arcs in the entire graph, which is the feedback arc number. So this gives us that the number of edges from R to L is at most opt. Now we can solve these two small parts, since they only have n over 2 vertices, optimally using the algorithm I mentioned before. And then we just combine the two solutions by placing the vertices of L in the computed order and then the vertices of R in the computed order. Both of these solutions combined are at most opt, plus the number of arcs from R to L, but this is of course also as most opt, as we discussed before. So this gives us a solution of cost at most 2 opt. Okay, now that we have that, we're gonna use a fast but bad approximation to get a slightly slower but still better than 2 to the n algorithm that gives us a better approximation. And we're gonna do this repeatedly until we get a approximation factor as good as we want. So the goal is to get a 1 plus epsilon approximation, and we're gonna achieve this by boosting our algorithm from a 1 plus 1 over k approximation to a 1 plus 1 over k plus 1. And in the beginning, using our 2 approximation, we can start with k equal 1. So assume we have a 1 plus 1 over k approximation that runs better than 2 to the n time, where this delta here depends on k. And I'm gonna define a weird value gamma. This is just a solution to some weird equation that depends on the logarithm of 2 minus delta k. And I'm gonna define alpha as 1 over gamma. And I don't want to prove this here, but just know that gamma is a value that is at least 2, so alpha is a value that is at most 1 over 2. And now we're going to iterate over all sets L of size at most alpha n. And for each such L, we also know the rest of the graph R. And for this rest of the graph, we're going to run our fast but bad 1 plus 1 over k approximation algorithm. And this takes some running time. Moreover, for the set L of size alpha n that has the minimum number of edges from R star to L star, we're going to also compute the value of R optimally, but we do this only once. And this takes us time 2 to the 1 minus alpha n time. And then we simply return the best solution we found for all L, either by an approximate solution for R or for this one set L star, the optimal solution for R star. So what's the running time? Well, how many choices are there for L? This is roughly n choose alpha n. From the n vertices, we can choose alpha n vertices for L. And this can be analyzed to be this gamma to the gamma divided by gamma minus 1 to the gamma minus 1, and this entire thing to the alpha n. And this is bigger or slower than 2 to the 1 minus alpha n. So doing some math, we can show that this is 2 to the 1 minus alpha n, which is 2 minus delta k plus 1 for some small delta k plus 1, but this is still a value larger than 0. So we achieved our goal in terms of running time. We have an algorithm that runs faster than 2 to the n time. But what is the approximation ratio? If it's not 1 plus 1 over k plus 1, then we haven't achieved anything. But here we only have to consider two cases. The number of edges from R star to L star can be small, and here small means 1 over k plus 1 opt, or it can be big. So let's consider these two cases. In the first case, where A is small, note that we computed the solution for L star optimally, for R star optimally, and the number of backward arcs is the size of A star, which is 1 over k plus 1. The solutions for L star and R star combined are, of course, at most the feedback arc number because this is a subgraph of the original graph. So our solution is at most opt plus the size of A star, which is A1 plus 1 over K plus 1 approximation. So in this case, we are good. In the second case, where we have a lot of edges for L star, note that we chose L star such that the number of these edges is minimized. So for every set L of size alpha n, it holds that we have a lot of backward arcs from R to L. And here, if I say a lot, I mean at least 1 over K plus 1 opt. And now we can simply consider an optimal solution for some set L. Here we have the blue edges in an optimal solution. These are solutions for the graphs induced by L and R respectively. And we have the backward arcs. The backward arcs we can assume are optimal because we consider the L that corresponds to an optimal solution. But maybe we have not found the optimal solutions for L and R respectively. For those, we have only computed a 1 plus K approximation. But now note that whatever the optimal solution is, some fraction C of it are red arcs, and some fraction 1 minus C of them are blue arcs. And by our assumption, C is at least or is more than 1 over K plus 1. And the red arcs, we know we have the exact set. So for these we pay. And for the 1 minus C blue arcs, here we only have a 1 plus 1 over K approximation. But now we can just multiply this out. So this gives us C opt. This one here gives us 1 minus C opt, and this 1 over K gives us 1 over K times 1 minus C opt. But since C is larger than 1 over K plus 1, 1 minus C is smaller, well, at most K over K plus 1. And C times opt plus 1 minus C opt gives us opt. The K cancels out, so here we get a 1 plus 1 over K plus 1 approximation, which is what we aimed for. So this concludes the first example for feedback arc set. Here we get a an exponential time but faster than 2 to the n approximation scheme. The second example I want to talk about is the optimal linear arrangement problem, and here I want to give a 1.5 plus epsilon approximation better than 2 to the n or faster than 2 to the n in the undirected setting. And the formal statement here is the following. For any alpha between 0 and 1, I can give a 1 plus 1 over 2 times 1 minus alpha approximation. So if alpha approaches 0, this approaches 1.5. And the running time will be the running time for k n minus k cut and some function that only depends on alpha. And here the running time will be 2 to the 1 minus alpha over 2n. But if alpha is something tiny bit larger than 0, then this is a tiny bit smaller than 2 to the n. And that's what we are aiming for. Okay, so what the algorithm does, it first iterates over all k between alpha n over 2 and n over 2, and it computes the minimum k n minus k cut for this specific k. And now we're just going to say k star is the value that gives us the smallest cut among all of these values for k. And for k star, we have a set L star that has the minimum number of edges to the right side R. And we're going to denote these edges by E star. Now we can observe that the number of edges is upper bounded by opt divided by 1 minus alpha n. Why is that? Consider an optimal solution. We don't know what happens in the first alpha n over 2 and the last alpha n over 2 vertices, because for those we didn't compute any cut. But each of the cuts in the middle has size at least E star, because, well, if one of these cuts is smaller, then for this k we could have computed a smaller cut. But if each of these cuts has size at most opt divided by 1 minus alpha n, then they all summed together is roughly opt. So here, this will give us later, I'll go a little bit more into it later, this will give us why we have this factor of n here. So for the algorithm, we're going to solve L star and R star optimally in 2 to the size of L star and size of R star time respectively. And this will give us solutions pi L and pi R. And now we're just going to analyze them. Okay, we have the red arcs. These are the arcs between L and R. And we have the optimal solutions for L and R respectively. And without any further things, this will give us basically a 2 plus epsilon approximation, because the red arcs each contribute at most n, and the number of these arcs is at most opt divided by 1 minus alpha n. So summed over all of them, this will give us opt divided by 1 minus alpha. And the blue things together are also at most opt, so this gives us 2 plus epsilon, or 1 plus 1 divided by 1 minus alpha. But the deciding factor here, why we can get better, and this is why this does not work in the directed case, is if I have a solution pi r for the right side and pi l for the left side, I can also reverse one or both of them, and this gives me new solutions. So let's just reverse the solution for r. The size of all of these cuts within stay the same, but some of the red arcs become smaller and some of the red arcs become bigger. But now we can make a average argument and say, well, we're gonna pick the orientation, either pi r or the reverse, that minimizes the average or minimizes the total. And then on average, each of these arcs has lengths at most n over 2. And since we have opt divided by 1 minus alpha n times n over 2 gives us opt divided by 2 times 1 minus alpha, which is exactly this factor we claimed in the beginning. And the running time, again, is k or n times the running time for computing the cut, which is this, and the running time for solving R star optimally and L star optimally, which is this. And that's all I wanted to talk about today. Thank you for your attention.